Hey, welcome back to week 6 spatial statistics. This week we'll be talking about a bunch of spatial statistics tools like average nearest neighbor and high and low clustering, the GETIS or general G clustering, and then we'll talk about spatial autocorrelation and multi-distance spatial cluster analysis and some of these tools and how these can be useful in your analysis while you're working on different projects. So the first tool, which is actually referring to chapter 8 in your book 2, actually talks about average nearest neighbor. So what this tool does is it determines whether your data is clustered or dispersed. So it sort of like calculates the nearest neighbor index based on the average distance from each feature to its nearest neighbor, the neighboring feature, and essentially it spits out an index that says if the index is less than 1, which means it has clustering, and if the index is greater than 1, then the data is sort of random and there is no clustering. And there are several possible applications. You might be wondering why we need to do this. One reason to do this is to evaluate if there are let's think of an example in the city itself, like crime analysis, whether there is a cluster of crimes, whether your crime data or the 911 data that you collected has any kind of patterns, and maybe if you look at that data and do this kind of analysis on that, you'll be able to tell the reason. You may be able to identify the patterns and maybe counter them by actually increasing police beats or so on and so forth. There could be several different possible applications, policy level possibly. The same way you can evaluate the competition by quantifying and comparing the spatial distribution of various plants or species within a fixed steady area, and then it also, for example, if you want to monitor change over time, you can essentially evaluate these changes in spatial clustering for a single type of business, like a grocery store or something, within a fixed steady area over time. And then, using this, you'll be able to understand what is the average distance between businesses, given like a city or a market area or whatever it is you define as your steady area. And then let's actually go to chapter 8.1, the tutorial 8.1 map document, which you can open from your ESRI Press, ESRI Press GST2, which is located under Maps. Just open your tutorial 8.1, and here from here you should be able to actually get a taste of this tool, so to speak. You'll be able to work on this tutorial. So as I was saying before, this tool again is used to determine the set of features, whether they show a statistically significant level of clustering or dispersion. So what it does in theory is it measures the distance from each feature to its single nearest neighbor and calculating the distance of all the measurements. So the tool then creates a hypothetical set of data with the same number of features but placed randomly within the steady area. Then the average distance is then calculated for the features and compared to the real data. So then a nearest neighbor index is returned, which expresses the ratio of the observed distance divided by the distance of the hypothetical data. And this ratio, if it is less than 1, then the data is considered to be exhibiting clustering, and if the data or if the value is more than 1, and then that it is more towards dispersion or random. So again, as the book explains, the idea behind this tool is that the things that are near to each other are more alike than things that are farther apart. So which means there is some kind of clustering. It's sort of like, this is based on, or it is called Tobler's first law of geography. This tool is best used on point data, although it can also be used for line and polygon data as well. So it is most appropriate to calculate the nearest neighbor index for equal study areas. You have to compare apples to apples. So this method works best when comparing data occurring in the same area over time rather than different areas. So again, let's get to this. Again, we are working in a hypothetical example using the Fort Worth Fire Department. And again, we are asked to produce the spatial analysis project, and then we were given the data of EMS calls from 2007 of February, and then so let's open the actual tool, which is actually called average nearest neighbor. Which is under spatial statistics. Open that, and once you open this, you should see. So as you can see, we have a little help here, which actually says what the tool does. Again, we need Euclidean distance, and we need to actually know the area. Area is actually the numeric value representing the study area, so we need to find out what our study area is. So the study area in this case happens to be the study area of battalion 2, which is this one. So if you open the attribute table, there is a shape area, which actually you sort of need this because you need this area to be inputted into the tool itself. So I'm gonna just right click on this field and click on copy. Another thing we need to understand here is that the EMS calls are sort of like the subset of 911 calls. So if you actually turn on the incident calls and then turn off the EMS calls, you can see the entire data. EMS calls is nothing but a subset of the data of the incident data. So if you go to the definition query of the EMS calls, the incident types which are equal or less than, greater than or equal to 300 and less than or equal to 322 are actually EMS calls according to the data. So we are just using that definition on this layer and symbolizing that slightly differently. And we also have proposed stations, active stations, and so forth, which this data you're already familiar with. So here I'm gonna go ahead and actually change the confidence level to 95% because that's the most commonly used confidence level. What this means is that if our z-scores fall between values of -1.96 and +1.96, that means our data is just random. And if it falls outside those numbers, that means we have some clustering. So let's open up the tool. This is a pretty straightforward tool. We know what our input feature classes, which is the EMS calls from Feb 07. So let's input the input feature class, which is the EMS calls for 07. We'll use the straight line distance, which means it's the Euclidean distance that we are going to use, and then we do want to generate a report. And the area we know from the battalion 2 that it's this one right here, the shape area. We do want to eliminate the whatever is after the decimal point because we want to make it a whole number, and click on OK. So our report has been generated. So to access that report, just double click on this average nearest neighbor pop-up box, the blue one, and let's look at where it has been stored. It's actually in a temporary folder in your C drive. So again, if you want to access it, so if you can't if you forgot to double click on that, don't worry. It is under your Windows geoprocessing results tab. If you open that window, you'll see all the numbers you need right here. So I'm just gonna dock it here so that I can see them all the time, and then I'm going to make this slightly bigger so that I can fill in the box that I need to fill in. So this box here, the nearest neighbor index, is this ratio right here, which is the 0.749050. .749050, and the observed mean is 338.44, and expected mean distance is 451.83, and the z-score, which will tell us whether the data is clustered or not, is negative 12.116 or 117, and the confidence interval is actually, so I entered those values in my sort of my observation box or summary box. So let me show you what the report has generated. So the report opens in your browser. If you double click on the report from the results window, it opens up and it says that since our value is right here, negative 12 point something, which is a significant amount of clustering, there is a pattern here, and then it's gonna give us all the necessary variables that we are interested in, and it's gonna actually put it in the feet or the units that it actually belongs to. So that's how you actually look at the report and run the analysis and figure out whether your data is clustered or not. So the book also talks about creating a box plot for the same data so that you can see the data slightly differently. It's just going to create a new graph here for a box plot, and we're going to use the EMS calls. The value field is FEE, and here the book has a weird graph. That's not what the data shows, so don't worry about how it looks in the book. So let's change the color to what the book is asking us to do and click on next, highlight color. So essentially that's how your data is gonna show up as. Honestly, it's not really good to actually look at, but it's not too impressive. But anyways, that's what the book wants us to finish as part of the exercise. So good luck with your assignment, and let's move on to the next one, which is identifying the cluster values. So let's move on to identifying the clustering of values. So this general G statistic, which actually measures the correlation of high or low values over the entire study area, what it means is it sort of measures the specific distances, how high or how low the values are, and compares this to how high or how low the rest of the values are. It is called the general G because it deals with the entire study area instead of just rather than a localized area. So this tool measures the clustering as we talked about, and then it's to actually go into slightly the background of the tool itself. It's an inferential statistic, which means the results are the analysis. Results of this analysis are interpreted within the context of a null hypothesis. That's what an inferential statistic means. So the null hypothesis for this statistic actually states that there is no spatial clustering. That's our null hypothesis. We go into this assuming there is no clustering of the feature values. So what happens is when we get these values, p-values, z and p-values, which actually are spitted out as part of the model, if the p-value is too small and statistically significant, then the null hypothesis can be rejected. But if the null hypothesis is rejected, then the sign of z-score becomes a little more important. If the z-score value is positive, and positive, the general G index is larger than expected general G index, indicating high values for the attribute are clustered in the study area. So even if the p-values are rejected and the null hypothesis is rejected because p-value is too low, if the z value is positive, that means there is clustering in the area. So anyways, you can read more about it if you want, but this tool is not really that commonly used. It's a statistic tool. It's not really a tool that I use a lot, but still it's important to know about this tool if you want to prove that there is clustering instead of actually visual. If somebody is really pressing you about the clustering or your analysis using maps or visual analysis, you can prove your sort of your theory based on these kind of numbers. So let's move on to the exercise. Let's open up 8.2, and then here we can see that so some more information about the tool itself. This tool assumes that the features have an association because they have similar attribute values as well as being within the specified distance of each other. So this the input features for this tool should have an attribute demonstrating some characteristic or value associated with the location. So that's the difference between analyzing data and analyzing spatial data. They have to have a spatial attribute. So another aspect is that the distance over the general G statistic will be determined to be significant, which means you have to run this tool several times to determine at what distance is this statistic more significant. So usually for features such as service calls, it is best to actually use the fixed distance band setting and run this tool several times to determine how location is affecting the clustering of values. This is because one call for service has no effect on the probability that another call of service will occur in the same area. So a call for service to fight a kitchen fire today will have no relationship for a call for an auto incident in the next block that may happen next week. So when you run this tool multiple times for different distances, the highest Z-score corresponds to the point of maximum clustering. So again, in this scenario, we are working with the Battalion 2 fire department, and we will be analyzing at what level, at what distance is the clustering happening, and determine the maximum Z-score on the confidence level and the band distance for clustering. So let's get started. The first step is to open 8.2 and then zoom into an area that sort of exhibits some kind of like visual clustering like this one. So again, search for the tool which is actually called calculate distance band. Calculate distance. So calculate distance band from the neighbor count tool. So we'll use calls for service of above 7 as the input features and set the number of neighbors to 7 and click OK. Calls for service, number of neighbors is 7, and then Euclidean distance, let's use those values, and then click on OK. Once the model is finished running, double click on it to open the results window, and here you can actually look at the minimum neighbor distance, average neighbor distance, and maximum neighbor distance. So essentially what this means is we need to travel about, on an average you need to travel from any given point about 1,000 feet to actually find 7 neighbors. So what that means in terms of input values for your general G tool is that you need to essentially try values from 200 to 1200 at a interval of 200 foot in order to figure out which value you will get the maximum z-score, produces the largest z-score for the and you can determine where is the clustering happening. So let's continue doing that using the search toolbox. Find high low clustering general G statistic, and then the input value would be transfer service, input value field would be the FEE, and then we'll generate a report, and then we'll use the fixed distance band, and we'll use Euclidean distance, and we don't use a standardization, and we start with a distance of 200. So let's go ahead and run this and click on open the results. So as you can see, the G value and the Z value have been produced by this tool. If you want, you can open the sort of this report that was generated. As you can see, the z-score is 8.73, which is pretty high. So I just went ahead and ran this model several times. If you want, you can just like double click here and double click on the general G tool and rerun this model for all the different distances, the 400, 600, 800, 1000 and 1200. And once you run those results, what you'll find is that your distance of 200 is what produces the highest amount of clustering, or the z-score, which means there is significant amount of clustering at that level. So again, don't worry about the yellow triangle, the warning symbol. What it is saying is that about 379 features do not have any neighbors within the 200 feet bandwidth, but that's just part of the data, so don't worry about that message. But you do want to go ahead and run the rest of the values and actually fill the table. Once you fill the table, you can come back here and fill out the maximum and the minimum z-scores. As I know, the maximum z-score is 8.72 and the confidence interval is at 95%, and then the distance band that we came up with at which has the highest amount of clustering is at 200 feet. So I'm just gonna go ahead and update that and export this map and go back to my city view, the previous view for the battalion, entire battalion, and then export the map and get started with my assignment of 8.2. That's it. So welcome back to tutorial 8.3, checking for multiple distance clustering. Also known as Ripley's K function, examines the counts of neighboring features at several distances. So the Ripley's K function method of pattern analysis essentially measures the distance between different features to determine clustering, but unlike the average nearest neighbor index, it includes all the neighboring features in the calculation, not just the nearest one. And also it doesn't just base its calculations on just one standard band, but it actually checks for different distances. You can specify how many you want to check within a specific distance, but we'll get to that. So again, it's another way of analyzing spatial pattern of incident point data, and also in many so far in the feature pattern analysis, we have to use like a distance band, like we talked about, or a threshold distance, while exploring spatial patterns at multiple distances and spatial scales. Patterns change, so this tool is very useful identifying those. So essentially, looking for clustering at different distances. When using this tool, we need to specify the number of distances to evaluate, and we'll see how this is done. If you want more information, just look at this how is look at this link. We won't go much into the details because again, like I said, this is a merely statistical tool, but we'll do it as the book requires us to, sort of like, again, we won't, as real estate people or real estate analysts or property managers, we don't really use this level of statistics. What we use mostly is visual and spatial analysis and network analysis, which we have already finished. This is just additional information that would help you sort of like look into the world of statistics a little bit, but not too much. So let's look at this scenario where we are trying to work with this data, again the fire department data that we have, and we will work so we will run this analysis for a set of distances and determine the maximum z-scores and confidence level and distance band for clustering. So again, the data is the same more or less. So let's go open map 83 and search for essentially search for the tool which is called go back to the search tool and multi-distance spatial clustering, spatial cluster analysis. Let's open that tool up. So for the input feature class, again we are analyzing the service calls, the output table. Let's save this under my data, call it k function perhaps, and then use the 10 bands and then use the display results graphically option, and the weight field again is actually the FEE, beginning distance of 200. It might actually think a little while before it actually lets you input the other values, so hang in there. And then the interval of 100, which means it's gonna go on till 1100 or 1200, and we're gonna choose boundary correction is none, and minimum user provided, study area feature class, and the study area we know is for battalion 2. So we're gonna select all the options, click on OK, let it run. So let's close this graph and go to our k function table, open the table, and from here we'll create a graph for the for the k function table, the value field being differential k, and we'll use the line, vertical line graph, and then we'll use the differential k as our y field, and the x field will be none, and the x label will be expected k, and then the y label will be differential k, x-axis label y, and then we will add this to the legend, and then so I'm gonna hit next here now that I got my graph, and then click OK. Right click on the graph itself and say add to layout. Once it's added to layout, you can just like sort of like maybe resize it or something, and then add it to the map. So how to read this graph? As you can see, the graph shows a peak at view graphs, graph of function k, not that one. Let's reopen the graph to actually read it. So I found the right one, graph of k function, and here as you can see the values peak at the graph shows a peak at the values at 900 feet and also at 500. So essentially any of these values might be the point of the most pronounced in clustering. The main difference is that this set of calculations did not include the confidence envelope and that the permutations would provide. The confidence envelope is developed by running hypothetical random distributions many more times. So what we need to do is rerun this multi-distance spatial cluster analysis tool with confidence envelope. So let's go ahead and do that. Let's open up the tool again, multi-distance spatial clustering, and this time the only difference is being will compute the confidence envelope 99 permutations. So here I'm going to run the analysis for calls for service 07. I'm going to choose the same options as the book. The output table will be k function, envelope, maybe envelope, and then the main difference is that here we're gonna go with the 99 permutations, which means this is gonna test for 99 different permutations essentially. So it's gonna take a little while, possibly depending on how fast your machine is. It says it takes about 15 to 20 minutes depending on your machine, but it might be much faster than that. The weight field again is FEE, the beginning distance being 200 and interval of 100. The boundary correction method is none still, and we'll use the user provided feature class and then select the battalion 2 as our steady area feature class. And now we're gonna run this. Hopefully it won't take too long. So once this k function has been table has been created, you need to add a field, call it difference, and here what we're gonna do is calculate this field based on observed minus high confidence envelope, to find the maximum clustering distance. You sort of need to find the difference between the k index and the upper limit of the confidence envelope. So let's go ahead and do that. So once you get those values, what you'll do is create a new graph for it's a vertical line graph. For the y field is essentially the difference, the x field is optional, and x label will be expected k, and then we'll go with the default options here and then click on next, finish that. So add this to the layout. Essentially, if you are looking at this graph, it is pretty clear that the value of 400 right here is where the confidence envelope and the it's the peak of the graph essentially. So so essentially the difference between the two graphs being you used a much larger sample by using 99 permutations, and that resulted in a better result for you, giving you a more specific answer, which is that the clustering is maximum at the distance of 400. So again, that's tutorial 8.3. Let's move on to tutorial 8.4. So measuring auto spatial correlation, chapter 8, tutorial 8.4. So measuring auto spatial correlation involves not only using feature locations or attribute values alone, but both of them combined together. Again, this is typically done with polygons that contain summary statistic such as census data and density data. And it is important to note again that it does not show you whether there is identify clusters, but whether to it sort of like identifies whether there is a pattern of values across the study area that tends to be clustered, random, or dispersed. So again, the point data for service calls will need to be aggregated into polygons for this analysis, so that it will give us clusters of density. One way to create summary polygon data is to overlay a grid of set size to count the number of locations that fall into each one of these cells or grids. So this is what we'll be doing. Determining cell size again could be critical. If you actually just draw one grid on the entire study area, one cell, that would essentially ruin your entire analysis. So it's important to choose the grid size that will have the polygons with at least one point in them. So, but it also provide large enough range of values across the data set. Using the standard size of city block or 500 feet would be just acceptable for this exercise. So take the hint. We should take the hint actually. In this scenario again we are working with the same data. Let's go ahead and open the 8.4 document. Once you open that, we can let's turn on the grid, the 500 feet grid that was already pre-created for us. If we want, we can create this grid quite easily, but that's not the point of the exercise, so let's leave it alone. As you can see, if you open the attribute table, these are essentially polygons, little polygons that actually encompass the entire grid, entire study area, or the battalion too. So using this, we're gonna right click and click on join. We'll join the based on spatial location the service calls for Feb 07, and then we'll choose each polygon will be given a summary of numeric attributes that the polygon under which the polygon whatever polygon it falls under, and also we'll have a count field probably. So essentially it'll also create a count field. So let's just go ahead and run this, and we'll save this under calls for service Feb 07 grid. Maybe I'm gonna call it grid calls. Click on OK. So once that is done, what we're going to do is based on the results, this could take a little while depending on how fast your machine can go. As you can see, there is a count about 7,000 done. This is a 500 feet by 500 feet grid, so now it's done. But all these grid calls does not have data. Only few of them do. If you actually look at count, it's got to be greater than 0, which means all the ones without any data is not relevant for us, so I'm gonna say count is not null. Let's go ahead and say that. So once you actually run that run that query, you can see only certain grids have data or points within them. So that's good. This is the data we want. So now we can run the auto spatial correlation on this layer. So let's go ahead and find spatial autocorrelation. Autocorrelation, global Morgan's I, and then we'll select for the input feature class the grid calls and the input field being count, and then we'll generate a report, and then we'll use the zone of indifference for a method which actually states that the features within the specified critical distance of a target feature receive the weight of 1 and the influence computation for the feature. Once the distance exceeded, weights and the influence of the neighbor feature diminish with distance. Okay, that sounds good. We'll go ahead and use Euclidean distance, which is straight line, and then we'll use a distance band or threshold of 3400 feet. So again, that being 3400, the logic being that we need to find at least 7 neighbors, and that's about 7 into 5, which is 3500. So that's about 3400 feet. And again, the test distance starting with 200, and it will go on till the z-score peaks. Anyways, let's go ahead and run this model and look at the results. So that's been computed. So let's open the results. As you can see, the report file that is generated actually shows us that it is clustered. It's not significant, but it is clustered. The z-score of 1.754, and essentially the z-score actually tells us whether the data itself is clustered or not. So they want to go ahead and run this run this model for different distances, especially since I have run all these distances. I'm gonna show you the maximum distance, which is at 42, which peaks at 4200. I'm just gonna go ahead and run this analysis. So once that's run, as you can see, the value would be the z would peak around 4200. So I'm just gonna go ahead and open that report file. As you can see, the z-score is 2.75 compared to our 1.74 before, so it is significantly clustered at that distance of 4200 feet. So again, that's tutorial 8.4, and we'll actually update this. We'll insert a little text box that shows what is the highest z-score and and what is the confidence interval, and so on and so forth. As you can see from the results, that it's a 99% confidence interval, and then again, the distance threshold is 4200 feet. All that good information, put it on the you know what, why don't we just do this, copy this, and then we can essentially sort of like paste it into the map maybe. So that could be our result. Maybe if you want to add some more information, you can do that. like confidence interval and band distance and stuff. So anyways, that's tutorial 8.4. Good luck with assignment 8.4, and that's it.